Hello guys, so my name is Rahul Madhwani. I am second year AIDS student. My roll number is 26 and my PRN number is 124BTAI 1048. So I am going to represent Laplace transformation and my partner which is Ayush Mahanwar will going to represent first shifting theorem. In, in this presentation, you will know about the Laplace transformation and its first shifting theorem. Now, what is Laplace transformation? Laplace transformation is a mathematical operation that converts time domain functions into S domain functions, that is from f of t to f of s. It simplifies differential equation by turning them into algebraic equations. They are widely used in engineering, physics, and control systems. So, this is the formula, that is Laplace of f of t, which is equals to f of s, which is equal to integration with a limit 0 to infinity of e raised to minus st into f of t dt, where t is the time variable, t, s is the complex frequency parameter, and f of t is the time domain function, and f of s is the Laplace transformation of f of t. So, these are the common Laplace transformation pairs, in which Laplace of 1 will be 1 upon s, Laplace of e raised to at will be 1 upon s minus a, Laplace of e raised to minus at will be 1 upon s plus a, Laplace of sin at will be a upon s square plus a square, Laplace of cos at will be s upon s square plus a square. Laplace of sine hyperbolic at will be a upon s square of minus a square. Laplace of cos hyperbolic at will be s square upon s square minus a square. Laplace of t raised to n will be n factorial upon s raised to n plus 1. Now, I will explain the real life applications of Laplace transformations. Now, the first application is in electrical engineering. Laplace transformation is the backbone of many electrical circuits because it gives many differential equations. First is transitive steady state analysis. Now, example, when the switch is turned on in an RLC circuit, in the diagram in which I have given beside, the current does not immediately reach its final value. The Laplace transformation is used to solve this transit response quickly. It converts the differential equation like Laplace of di upon dt plus Ri plus 1 upon c integration of I dt into volt of t into algebraic equation in the S domain, which are much easier to solve. They are used to filter design. They are used to design low pass, high pass, band pass filters like radios, speakers, and mobile devices. Example, in audio equalizers, Laplace transformation help design filters that remove unwanted noises. They are also used in signal processing. Any periodic or non-periodic signal can be analyzed in frequency domain using Laplace. Example, in mobile communication, Laplace helps in modulating and demodulating signals. So, the third is mechanical and civil engineering. In mechanical systems, often deal with oscillations and vibrations. The first is vibrational analysis. Example, in car suspension model as spring damper system, Laplace transformation solves the equation of motion to design smoother rides. And bridge design and structural dynamics. Bridges and buildings under wind and earthquake loads are modeled as vibrating systems. Laplace transformation is used to predict resonance and avoid structural collapse. As shown in the diagram beside that, it shows a diagram model of a bridge which is made using Laplace transform vibrations. The third is damped and undamped systems. Example, shock absorbers in bikes and cars are modeled with Laplace to design the damping properly. So the above diagram shows the car suspension system with springs damper model. The This is the most common application. It is used in physics. Laplace transformation are widely used in theoretical and in applied physics. First, heat conduction problems. Example: cooling cooling of metal rod is governed by the heat equation PdE. Laplace transformation helps it solve efficiently, like the diagram I have given beside. The second is wave equation. Sound waves and electromagnetic waves can be analyzed in Laplace domain for easy solution. And the last is optics and quantum mechanics. Laplace methods simplify complex wave function equations.
My topic name is Laplace transform and first shifting theorem. The Laplace transform is a tool to solve differential equation, and first shifting theorem help us to handle the exponential terms more easily. In this presentation, I will explain the theorem, its proof, and simple example. Let's begin. This slide explains the first shifting theorem of Laplace transform. The statement states that if the Laplace transform of f of t is f of s, then the Laplace transform of e raised to at of f of t is equal to be f of s minus a, where a is constant and s is a Laplace variable. So in simple terms, we can say that by multiplying function by e raised to at in the time domain does not change the shape of its Laplace transform. Instead, it just shifts the transform along the s-axis by a. So basically, in the exponential term, e raised to at just replace s by s minus a, representing a horizontal shift in the transform domain. So now let's begin with next slide. So in this slide, I'm going to talk about proof of first shifting theorem. We know that the Laplace transform of function of t is integral 0 to infinity e raised to minus st f of t dt. Let's consider Laplace of e raised to at of f of t. So the Laplace transform will be integral 0 to infinity e raised to minus st multiplied by e raised to at f of t dt. So the Laplace transform will be 0 to integral 0 to infinity e raised to minus s minus a t f of t dt, which will become function of s minus a. So thus Laplace of e raised to at of f of t will be function of s minus a. Similarly, for e raised to minus at, it will be f of s plus a. So now I will go into talk about some simple examples. Here is the example of first shifting theorem. In this example, we have to find the Laplace transform of e raised to 2t sin t by using first shifting theorem. So we first will recall the Laplace transform of sin t, that is 1 upon s square plus 1. And now we will apply first shifting theorem, that is Laplace of e raised to at f of t is equal to f of s minus a, where in this we can see the f of t is sin t and a is 2. So f of s equals to 1 upon s square plus 1, where f of s minus 2 will be equal to 1 upon s minus 2 ka whole square plus 1. So the final answer is Laplace of e raised to 2t sin t equal to 1 upon s minus 2 the whole square plus 1. So here it is a new question of first shifting theorem. In this question we have to find the Laplace transform of t cube multiplied by e raised to minus 4t by using first shifting theorem. So first we will recall the Laplace transform formula for t to the power n, that is n factorial by s raised to n plus 1. Here we can see our n is 3. So the formula will become 3 factorial by s raised to 4, which equals to 6 by s to the power 4. So now we'll apply first shifting theorem formula. So first shifting theorem formula is Laplace of e raised to at of f of t is equal to f of s minus a. Here our f of t is t cube and a is minus 4. So f of s equal to 6 by s to the power 4, and f of s plus 4 will be 6 by s plus 4 the power 4. So the final answer is the Laplace transform of t cube multiplied by e raised to minus 4t will be 6 by s plus 4 whole the power 4. So here it is a short conclusion on first shifting theorem. So in simple words, the first shifting theorem says that if we multiply a function by e raised to at, its Laplace transform just replace s by s minus a, and this makes us to solve the, or we can say easily to find out the Laplace transform of exponential term without doing any integration. So this is the by end of the slide. Thank you.